Hello, this is Dr. Stephen Bartlett, and today we're going to be talking about contour maps and watersheds. These are important concepts that we're going to be using sometime during this semester. So I'm going to give you a basic introduction to how to do contouring, make cross sections from contours, and then also how to delineate watershed maps. So let's spend just a moment on the learning objectives for this particular lecture. We're going to understand how to interpret a topographical map. We'll discuss briefly some of the common symbols used on topographical maps, learn how to draw contour lines given a set of elevations coming from some type of survey, understand how to take that contour map, make a cross section through it so we can understand the profile view of the terrain. Then lastly, we'll spend some time delineating a watershed map. Just want to remind you that this is an individual assignment. This is not to be done in teams. You can certainly ask a friend or anybody that you want to assist you, but it still must be your own work. What we will do in the first exercise in developing a contour map is we'll be given a set of data that has elevations, and we'll take those elevations and learn how to hand sketch contour lines at 400-meter intervals. Then also important to doing that is to label the contour intervals. We will select a 400-meter interval, meaning that each contour represents a 400-meter change in elevation. We'll label all the contours that are on the contour map, and then I ask you to submit that map as a JPEG or PDF file to Canvas for grading. Also, we'll create a cross section from the contour map that you create. I'll show you that section in just a minute, and we will use that to develop a profile view of the data so that we can see what the terrain looks like along a specific line. Then lastly, I'll talk about how to delineate a watershed map. Again, it's coming from contour data. And for the particular case that we're going to be using, we'll focus on Red Butte Canyon, which is near the University of Utah. And lastly, also for like the previous two exercises, these would be submitted as JPEG or PDF files. So the homework, the first two exercises for the contour map and the cross section will both use the same set of data, so you want to make two copies of this if you print this out to be used by hand. The first thing that you notice on the map is a bunch of digits or numbers which represent elevations. So the units on this particular drawing are in meters. So we can see the high point, I believe, in the map is somewhere about here at 4097 meters. So using this elevation data, you will develop the contour map from these points, and that's explained how to do that later in the lecture. For the second part, for developing the cross-sectional view, we're going to do it from line A to A primed. So we're starting at elevation 1979 and going up to this on this line to elevation 1490. So the process of how to take the contour data and project the elevations onto a straight line and then develop a profile line is explained later on, and I'll give you more instructions about how to do that. In the notes, I've given you a kind of a typical cross section. This is not what would come from your results. This is not a profile line from your results, but it would look similar to this, so that we notice over here we see the elevations here. This is the elevation axis. This is the distance axis down here. And we have points that have been projected on the cross-sectional line, and then we connect those dots to give us what the profile line is. So think about this as if you were on a hike going along that straight line, and as you traverse that line going maybe in either direction, you would have changes in elevation. So this would give you the grade or the change in elevation you'd have as you continue along that line. So embedded in the lecture notes, I've given you a video that explains the process of how to take elevation data and to develop a contour map. So please watch this before you attempt to do this homework. I think you'll find it informative. So here is a topographical map of the Salt Lake Valley. I'm going to zoom in here just to give you a little bit of idea of what's on the map. We see the rivers that are indicated here by blue lines that go through the valley. The heavy black lines are roadway systems, at least the primary roads. These brown lines then form the contour intervals. So it's clear, you know, at least when we look at the topography in this area, we have a gentle, large valley basin here. It is gently sloping on the west side. On the east side, we have some benches left by Lake Bonneville, and then we're into the terrain that forms the canyons. These lines here that are white are the lines that show the valley. Sorry, my photo's distorting here for some reason, but we can see the lines here that show where the streams come into the valley. So as these brown lines get very close, then that means the topography is a very steep terrain. As we discussed in my introductory lecture to this class, we saw some examples of digital elevation models. So this type of rendering takes different elevations throughout the valley and renders them so that we see what the terrain might look like. This is artificially done. This is not actual aerial photography, but we get the impression that it is somewhat real. In this case, they've even taken some of the higher elevations and dusted them with snow. But anyway, it still gives us a good idea of the terrain around the valley in a very visual way. Unfortunately, because there's really no elevation data directly on this map, it's not that useful to us. However, the elevation data that was used to create this map is usually contained within some type of model. Okay, let's spend a few minutes talking about how to read topographical maps. The things that we want to learn here on this particular slide is how the contours let us visualize the terrain. We want to talk about how map scales work and other useful map details. And then lastly, I'll make some discussion about where we might find topographical maps. Okay, so let's go down to these examples we see here. We have a hillside here. It represents a relatively steep slope. So the contours that we see in this part here are quite close together. As we, would look, from a line along here, we would go up a significant grade or increase in steepness as we go up towards the peak. If we maybe then continue that line from here on to the other side, even the contours in this area now are even more steeper. So that would be reflected by a steeper slope that we see here on the downslope side as we come from the top down to the bottom. So we are looking at a 2D, what we sometimes would call plan view as engineers, but geologists would call this a 2D map view in this case. And then this is a 2D profile view. Or sometimes it might be also referred to as a cross-sectional view. Okay, let's spend just a moment with this other hillside here. Looks like if I move the slide, then I move the labeling, but I guess they're both the same. Let me just erase these lines here for a minute. Let them disappear. And so we still have a 2D map both profile and cross-sectional view. In this case, let's say that the contour intervals for this particular map and this particular map are the same. If they are the same, then the fact that this slope here has less contours means it has less elevation change, it's less steep. So as we look at the contour lines, then they're closer together. So if we were to hike from here to here, we'd be going up a more gentle slope as represented right here. And then if we continued our walking, we would go here and we go down the other slope down the other side, which, like the previous example, the slopes on the right hand side of both of these mountains are steeper, as shown by the contours that are closer together in this region here and the closer contours that are together in this region right here. So let's look at these two mountain sides here. We have two peaks that are close to each other. This is similar to what we saw on the last page, and we notice that the contour lines are steeper here, and then the peak is represented here. Since the contour lines are less close together or further apart, then this peak is going to be less. Also notice that because there are more contour lines and these are at the same contour interval, then we could count the contour lines and kind of infer how steep something would be. So if we were to look at these mountains here, in three-dimensional kind of view, then we see the steeper mountainside with the higher peak and a lower mountainside. Let's talk about the importance of contour intervals. So in this map, the contour interval is given to us right here. It's 80 feet. And so each time we change and go from one point to another across these contour lines, we're going up 80 feet in elevation. Quite often too, what we do is every fifth line, so this is a line right here and another line up here. If we count how many contour intervals are between them, we'll skip this line, we go to this would be one interval, two intervals, three intervals, four intervals, and five intervals. So there's five intervals between them. So if we take 5 times 80, which is 400, we then do check that there is really a 400-foot difference between that point here and this point up here. Okay, so that's to keep in mind that quite often maybe only the major contour interval, the one with the heaviest line, might be labeled. The minor contour intervals will not necessarily be labeled, but we can figure out what is the change in elevation by knowing the contour interval itself. Once in a while we have to represent depressions, and so instead of going up, the topography is going down. So this might be some type of pond or lake bed or depression that's in the terrain, and so we can indicate that by using these hatch marks here. You can see one right here. So that indicates we're going down and not up. So it's a common thing to keep in mind. These don't occur that often, but you may see them once in a while, particularly if you get into terrain that has a lot of swamps or lakes or things like that that we need to interpret. So as we get into maps that are produced by the U.S. government, primarily the United States Geological Survey, they have a standard set of symbols that show up on a map, and also there's a set of a legend that shows the different types of features that might be present. So let's just spend just a minute with them. The map scale shows you the distance. These are drawn directly on the map, so if you needed to, you could take a ruler or scale and you could use this scale here and then transfer and measure some type of similar distance on the map. So this is done quite frequently, and you can buy particular scales that are commercially available that allow you to scale directly distances off of the map. it may be useful sometimes, particularly if you're hiking or doing other types of things where you need to know distances. So this scale is 1 to 24,000. What it means is 1 inch equals 24,000 feet. This is a common scale used by the USGS. So if you find that you'll find hiking maps and other maps that you use are based on USGS base maps, and they'll have this same type of scale. Once in a while you'll hear this referred to as a 7.5 minute quadrangle map. That just means the type of size of the map in terms of a surveying quadrangle. Let's just look at a few of the details that might be on a map beyond just the scale. These are symbols here that would show national versus state park versus maybe private lands and things like that, so you would pay attention to them. There would be symbols that would show features like campgrounds, picnic areas, so on and so forth, ranger stations, shelters. This sign here shows the north arrow, so by convention north is pointing towards the top of the page, and then this arrow here shows magnetic north. So magnetic north, if you're using a hand compass, is occurring about 16, I guess, 0.01 degrees, or maybe 16 degrees, 1 minute east of true north. So this is referred to as the declination. I have a compass that I can adjust rotate my inner degrees within the compass itself so that I can read true north and true bearings and azimuth without accounting for the declination. But it's an important thing to keep in mind that the declination isn't constant. It changes throughout the United States. So whenever you get a USGS base map or something, it's important for you to figure out what is the declination if you're going to be making changes between true north and magnetic north. This scale here is different than 1 to 24,000. This is the next size up, the next largest map that the USGS produces. It's a 1 to 69,500, almost 1 to 70,000 scale. And this one also reminds us on the map that the contour interval is 80 feet. Gives the date that it was issued, and any date it might have been revised. Okay, so that's just a quick overview of some of the things that you'll find on a map. I believe in the introductory lecture I gave you 2 pages of common symbols and things that would find themselves on maps produced by the USGS. So drawing contour maps takes a little bit of practice. That's why I encourage you to use pencil when you draw on the elevation data that I've given to you. In case you have to erase any lines, it's easier to have it done in pencil. So this video here that's included in the notes will show you the step-by-step process of how to develop contours from elevation data. So please watch this before you attempt to do the homework. So let's take an example map. This is similar to what's in your homework. It's not quite the same, but this is a volcano in Hawaii, and I believe your homework is also from a volcano in Hawaii. So as we look at this, in general of the major features, we see that we do have the scale listed here. It's important we see the north listed here, so remember to include those on your map. And then we have the contours that have been labeled here to the major peak. Some of these contours have been continued on the back side of this main crater or volcano. So let's think of about something that might be missing on this map. I believe if I were to do this, I would probably think about putting some type of, elevation right there. I'm just going to write an ELEV. That would be a nice thing to know. And also, I'm not sure it's necessary to make a contour line down this way and add the labeling, not the contour line, excuse me, a set of elevations similar to we see here, label them down this side That would be kind of a challenge because they would be close together, but maybe an idea is to label maybe every fifth one or so, starting with one at the peak and then skip 5 and label the next, so on and so forth. So that might be an improvement, but not a major problem with this map because we can still pretty much figure out what this is. Though it's not shown on the map, let's zoom in just a second. I don't think I see the contour interval here. So it looks like it's every 1,000 feet. So maybe just to help people along in your legend down here, you could just write, you know, like CI for contour interval equals 1,000, I guess it is. I'm pretty sure those are feet. Okay. So just remember, for completeness, it's not enough just to do the contour itself. You need to have the critical features of the scale, the northing arrow, and the contour interval. So in part 2 of the homework, we're supposed to develop a profile line. So let's look at that in a minute. I'm going to talk about this drawing down here. There is a video that shows you how to do this. It looks a little bit different in color because I've got the colors inverted when I'm doing this light board so that the black and white really show out. But anyway, please watch that. It'll explain how to develop a profile line. So in this case, we're going from point A here over to point B here, and we're taking a line that goes along this horizontal line that connects between the two. Okay, so that's somewhat messy. I'm going to get rid of that, but that's just what we're doing. So obviously we can't do the profile line until we have the contour lines, because the contour lines give us what would be the projected or inferred elevation, estimated elevation at each point along this line. It's not very common that we would have elevations along a straight line in anything that we do. So remember that these contour elevations where they intersect the profile line are being inferred by the process of contouring. So it's perfectly good to go ahead and use the contours that you develop in the first part of the assignment to do the profile line in the second. Then the next thing we do is project those elevations down to a profile line. So think about, you know, this is again map view or plan view, and this is in profile view. So we have adopted a vertical scale here. It's shown up right here. You can see 50, 40, 30, 20, 10, and then 0 would be down here. And so as we adopt that scale, we need to make sure that it will at least anticipate what would be the highest point on the map, so that we have enough lines here, horizontal lines, to represent the maximum elevation on the map. All right, so then once we get a line established between point A and point B, then we simply transfer those lines. We don't have, up here in this map, we don't have anything above, we don't have a 60. There's, if you notice, there's no, at this point, there's no 60. It doesn't exist. So we know that that elevation where it crosses the profile line is below 60, and that's an important point. So don't try to infer something that's not there. It's not there. So basically then we have a circle around the peak, but we don't know the exact elevation of the peak. So in a way, this point right here on the profile line is somewhat an artistic guess. It's not exactly known, but it would never go above an inferred 60 line here. Okay, so just keep that in mind. All right, so as we get, you know, cross an elevation, or excuse me, a contour along this map, we just project that straight downward to the scale that we developed on this, and we would plot a point there representing an elevation of 10. As we cross the 20, we project that down to this point here, and we just keep on doing this, projecting these lines from this map view projection down to the profile projection and plotting points. Once we get those points all plotted along this line, then we simply would come in and draw a line to represent the profile. Let me get the rest of them here as I go off of the light board, and then I'll maybe hide this projection. Let me move it out of the way. So now I have the points that represent the different elevations. So I just simply kind of just use my hand and hand sketch them in and draw a profile line. Okay, so that's a fairly simple process. It'll take some time to do it, but remember, we're just doing a straight line projection from the contour lines down to the profile scale. So if you're following along in the lecture notes, you'll notice that I've skipped a page. On the previous page was still a link to a video that you can watch regarding watersheds. So I would encourage you to also do that as you go through the lecture and prepare yourself to do the homework. So let's just briefly define a watershed. So if we look at how water flows on the surface of the earth, obviously it falls from the highlands or the high ground and eventually finds its way to maybe rivers or to the ocean or to the lake in the low spots. So we can see in this particular diagram here, we see the highlands that are marked, and then we see drainages that come down through to a central valley to a major river that might be flowing into a lake or the ocean. I'm going to do a little bit of lightboard magic. I can't draw directly on this white page, but I can invert the colors and draw on it this way, so don't mind my inversion of the photo. It makes it so now I can draw on the lightboard. So the important thing then is to understand, if we were to look at this, maybe drawing with my mouse, I got to remember I got to use my hands when I do this. Let me yeah, you can't see behind me too much, but if we come here on the light board, let me try to fix something here. I'm going to add some transparency here so I can draw. Maybe that will work. Okay, so now, yeah, now you can see my hand come behind. I'm just learning how to use this, so excuse my kind of beginning, attempts at this. But we see that feeding into this major river system, there are side streams and channels that come into it, and we see a terrain that has mountainous as we go into the background. So the idea is, well, if we were to look at water, if we looked at a drop of water here on this mountain, it would certainly go that direction. Water has to go downhill. But if we were to put a drop of water on this side here, then it would go down that way and eventually end up into the river. So the point where of the divide, think of this kind of like a mini continental divide, if you want to think of it that way, is right at this point defines the point where a drop of water hypothetically would not go either way. Well, we know that that's just a simple point, and it would go either this way or that way. So this defines a dividing line. So if we look here, it's kind of in green. We can see this dividing line that goes up here that divides the terrain, so that water on this side flows that way and water on this side flows this way. So these are high points or ridges that you would hike up, that you would, if you wanted to go follow the high ground before you reach maybe this peak here. So just think about hiking along the ridge line, and in a way, by doing that, you are then following the watershed boundary. As we get to the back of this drawing here, we see a higher central peak. So we're going to assume that we can see kind of the ridge line that's going here. So we're just going to connect the watershed boundary up to that peak. Because remember, everything that's still in this line that I'm drawing would still drain through the channel systems and eventually into the river. And we'll follow it down here. It will be followed here, go up and get that other peak, and then eventually be a ridge line much like we saw on this side here. Would be following and going down this side here. So everything that falls within this boundary finds itself into this, maybe to this point right here, or this line here. Water has to flow through this, and it's coming from the tributaries or off of the slopes, running into this and feeding into this watershed or water basin. So obviously this is very important for many aspects in engineering. It defines how much, if we have rain in this area, how much rain might eventually find its way into the river system. So it's important for hydrological studies to understand flooding and other things. Also, let's say that there's some type of contamination that falls for some reason in this zone. We can then predict, what part of the watershed it might affect. Or maybe this zone here was a wildfire, and we can predict maybe how much damage that has done to the watershed, and or how much additional runoff we might get from the wildfire zone due to the loss of vegetation. So there's many uses of this type of information. So it's critical that you learn how to do this. So the next 4 pages in the lecture notes continue to give you instructions of how to delineate a watershed boundary. I'm not going to take the time to cover that. I'm going to go ahead and discuss a little bit about Red Butte Canyon and maybe get you started on the last part of this assignment. So I have a low-angle aerial photography here coming from Google Earth of the canyon, and I'm just going to use this to help me probably visualize a little bit better what the canyon looks like. So I'm going to think of maybe the outfall starting somewhere maybe in this point down here, and then obviously up here you can see there's quite a prominent ridge line that comes along, which would define what the boundary is going to be on the kind of south side. So I'm going to have to turn down the instructor light so I can see this a little better, and maybe I can then help do this. So I'm identifying some points that are definitely in the watershed boundary. It looks like this canyon, the ridge line goes up here and then follows up this way into the highlands. Now I can't really tell what's going beyond here in the upper ridge line. There may be some detail I'm missing in this photography, but I believe that it's going to follow up something like this and then come down the ridge line and start coming down this side here like this. I'm going to stop because of the shadow. I can't see what's going on, but you can kind of get the idea. And then starting on this point, it's going to follow down this ridge line like this. Like this. There's going to be probably a jog here, and then I'm going to come down here, and then I need to drop back to my outlet point, something like this, because at some point water on this side is going to start flowing into that side canyon. I don't want to capture that. You'll find that on both sides. You're going to need to kind of neck in the watershed map. So a lot of what you need to do is figure it out here. I'm not sure I've been very precise here. I may have some reasonable estimates here, but I may go in and develop a video in Google Maps to show you how you can use the terrain in Google Maps maybe to help figure this out a little bit better. I hope that's useful, and we'll see you later. See you next time.